In this video, I'm going to demonstrate how to compute the R-squared and then also the results for the Anova table for a linear model by hand. I do this because I think it's important to realize, hey, this isn't magic, what's happening. Everything is a bunch of ratios and it can be computed or calculated, right? So we're going to use the same example we used before with the relationship between fiber and potassium. And we're going to go ahead and load our dependencies. And I'm just going to build that first model that we've already built, where we say fiber is the output, potassium is the predictor. And we can see that mod. And there is our intercept, our first parameter, and our second parameter, our beta or our slope, right? Now, we can also create a null model. And a null model would be, probably the simplest is if we were to just use the average, where we say, you know what, take the average of fiber, don't worry about any predictors, and that's the model. Whatever the average is, that's what we'll say is going to be fiber no matter what, right? So that's the null model. That's what we're going to be comparing against. So again, we can look at the betas, the summary of the betas. Here we see the omnibus results at the bottom. Residual standard error, we see the multiple R squared, the F statistic, the p-value, and some of this may look like magic, but it's really not. It's all a bunch of ratios, right? One thing I do want to point out is you can compare different models. So we can use the Anova command right here on our model, right? And it will automatically compare it to the null model. But the Anova function is actually pretty useful for comparing multiple models, particularly as you get into multiple regression and other coursework. And what you can do is pass it nested models. So here we have mod, which is our linear regression model, and we have the null model, which is just the average, right? And we can use those, we pass them in as arguments to Anova, and it will compute the differences. And we see that, yeah, there's a significant difference between these two models, right? And that's essentially what the Anova is doing on just mod. It's already comparing it to just the null model. It's okay if you don't really quite get this in Anova for comparing multiple models right now, but as you progress in your learning, that can be pretty useful. All right, so let's go ahead and plot these residuals. And we're going to plot the residuals for the linear model for, so let's open this up in its own window here. And what we see here are the regression line, that's what we predicted for these values, and then the points are the actual values. And you can see the blue dotted line going down to the regression line. Those are the residuals. That's what we said was going to happen, the prediction, minus the actual values, right? So these are just error terms of the residuals, right? And this is for sum of squares error. We can also plot the residuals for the null model, which is mean. And I'm going to get a little more real estate here so you can see the code for it. And you can see that I've passed in a formula. So up above, we use geom smooth and we use method equals LM, right? Well, here you can pass in method equals GAM and then formula equals Y tilde 1. And what that says is don't use any predictors, just go ahead and use the mean. And I computed the difference for the segment of the difference between that mean and the actual values. Let's go ahead and open that up. And we can see here the residuals if we use the mean as the model, right? So this is the null model, and this is the sum of squares total, right? This is pretty much as bad as you could get, or the minimal amount of badness for a prediction is if you use the average. I guess random guessing would be worse, but so this is, our model should do better than this, and significantly better, right? So let's look at those two models together, both the null model, which is the average model, and then the linear model. Okay, so you can kind of see how they do against each other. It's a little bit overplotted there. So really what we're interested in is the difference between the null model, the sum of squares of the model. So these are the orange dotted lines. We're interested in these, the difference between the null model and our model, right? So that's what you're computing when you run Anova on your model, right? So let's start breaking these tables down a little bit, and we can also do summary on mod. And here we have the F statistic and R squared. So let's break this down, this tables down a little bit. Now the first thing we're going to talk about is N, and this is the number of observation. There were 77. And in P, this is the number of parameters that we're estimating. And we're estimating beta and intercept, so that's 2 parameters. And now the degrees of freedom for the model is just P minus 1, so that's 1. And the degrees of freedom for the residuals is N minus 2. 75. All right. Now, let's start computing some values. So we have the Broom argument. I'm going to get a little more real estate here. And you can see that it gives us the original data, the fitted. We're not really at this point interested in all of these, so I'm just going to go ahead and add the serial name back in. I'm also going to take the average of fiber. That's the null model. And then I'm going to compute the error for the null model, which is just what fiber is, minus the average. That's what we have here. Then I'm going to also compute the linear model error, which is fiber minus the fitted value right there. That's what we predicted, right? And I'm going to select just the columns we're interested in. and I'm going to turn it into a table so that it's easier to view. Okay, so you can see what we've computed here. The average is just 2.15 for all fiber. The average error then is fiber minus the average, so 2 minus 2.15. Okay, and then we also computed linear model error, which is your fiber minus your fitted. Gives you this. Okay, so the next thing we want to do is figure out the sum of squares of these errors. And we want to do that for both the linear model and the null model. And so what we're going to do is go ahead and square every single one of those values to get rid of the negatives, and then we're going to go ahead and add them up. So that's sum of squares error is for our linear model, sum of squares total, that's how bad we can possibly do. Basically, baseline to compare against. We're going to go ahead and compute summaries for those. So we have sum of squares error and sum of squares total. And now from there we can compute the sum of squares of the model, and that's just sum of squares total. So that's what we're interested in again, right here. This is what we're interested in. And so to get sum of squares of the model, it's just the difference between sum of squares total minus sum of squares error, which is what we have right here. And then to compute the r squared, it's just the ratio of sum of squares error, that's of our linear model, divided by how bad we could possibly do. And this is a proportion, so we do 1 minus that. We can compute the mean square of the model by taking sum of squares of the model divided by the degrees of freedom of the model, which we've just computed all this already. Remember, degrees of freedom is number of parameters minus 1. And then we can compute the mean square of residuals by taking the sum of squares error divided by the degrees of freedom residuals. And remember, that's just n minus 2. And then the f ratio is just the MSM divided by the MSR, right? And we're going to go ahead and round all those to 2 digits. So let's see what that looks like. So we just computed all those items. We can look up to see if this is indeed significant, the f result, which I can tell already it's huge. This is for 0.05 alpha, and there's 1 for the first degree of freedom, and then 75, and so a value anything greater than 3.97, and I'm pretty sure that 332 is much larger than that, so it's a huge p-value. We can also use r to look up the p-value using the pf function. Again, very small p-value. We can compare this to the Anova table, and we can see here are the values we just computed. Here's the Anova table, and we can see all the different pieces. So this is the degrees of freedom up above, that's parameters minus 1. Degrees of freedom of the residuals is n minus 2, sum of squares. Right here, 352, sum of squares there. And we have sum of squares of the residuals. See that there is the SSE. And then all you do is to get the mean square, you take sum of squares divided by the degrees of freedom, which you get here and here. So basically it's this column divided by this column gives you this column. And then to get the f statistic, we just take mean sum of squares divided by mean sum of squares of the residuals, gives you the f statistic, and then the p-value is given to us here. It's also very small. That's how you compute all those values from the Anova table. So what this tells us then, again, is this. How much better is our model at predicting fiber than just taking the average of fiber? And again, it's just a bunch of ratios. There's nothing magic about these Anova tables. We can compute all those values ourselves.